Now the second one that we're going to be looking at is the partial fraction expansion, second method. So method number 2 for getting the inverse Z transform is partial fraction expansion. Fraction expansion. This is also very similar and simple like the first method. Okay, and we would like to see how we can exploit this this particular technique so that we can get the benefit of that. Okay, so we look at a Z transform which is in rational form. Summation k equal to 0 through m bk z power minus k divided by numerator polynomial by denominator polynomial k equal to 0 through n ak z power minus k. So basically this is a rational form. Okay. Then what we will do is we're going to pull out b0 as a common factor. Then what will you get? K equal to 0 through m bk divided by b0 z power minus k, and here I am going to pull out a naught summation k equal to 0 through n ak by a0 z power minus k. Okay. Now notice what happened to the first coefficient k equal to 0. You get b0 by b0. First coefficient becomes 1. Similarly, the denominator, the first coefficient becomes 1. So now what we can say that this can be written as b0 by a0, a scale factor, times a product of first order terms k equal to 1 through m 1 minus ck z inverse. Denominator, product of k equal to 1 through n 1 minus dk z inverse. Okay. Now assume that you have a proper rational form. Proper rational form. Okay, which means that m is strictly less than n. In such a case, you can write h of z as a sum of n first order terms k equal to 1 through n ak divided by 1 minus dk z inverse. Okay. And once you have it in this form, then you can immediately write down the ROC. You can look at it. If you want a right-sided sequence, what will it be? Max over k of dk. Okay, so that will become your reference point, and the ROC will be mod z greater than the maximum. So basically whatever is the rightmost pole, you take it outside of that. So then what we get as the corresponding time domain sequence will be h of n equal to summation k equal to 1 through n ak 1 by dk raised to the power n u of n. Okay, so that, and you will get such terms, and that will be your now what did we do? We took the rational form and said that if it were a proper rational form, then we can write it as first order terms. You have to compute AKs. Okay, so in this step we have to compute what these AKs are, but that's a very simple procedure which we can do. Once you write it down, you can solve for those equations, and then you can get the expressions for what we need to do. Okay, I hope you are comfortable with that, and this is what we need to do for proper rational form. Now, if it is improper rational form, improper rational form. Okay, then which means that m is greater than or equal to n. Then what we do is we write it as basically go through the process of writing it as in terms of as a long division you can do. Eventually you will write it in the following form. Okay, h of z is equal to summation r equal to 0 through m minus n. Okay, m minus n, those are the that will be the terms that will come out when you do the division. Okay, we'll call that as br z minus r. Okay, and the remaining ones will be a proper rational form. Proper rational form. And proper rational form we know how to do, so I'm not going to write it all over again. So now this is something that you must capture. This will be some corresponding h of n will be summation r equal to 0 through m minus n br delta of n minus r. Okay, so basically these are constant coefficients. They will occur as delta functions with the appropriate delay, plus the corresponding the h of n, the inverse z transform of the proper rational form, which we know how to get. Now, the only thing that we have not touched upon in the context of partial fraction expansion is if we get repeated roots, because this form that we have is valid. This form is valid if all roots, if all decays are distinct. Distinct means there are no two roots which are equal. Okay, that equal. Now, supposing you have a situation where you have repeated roots, then what you do is you take out the portion where you have no repeated roots, and then the part that has got repeated roots we will handle in the following manner. The part, let us say that if there are repeated roots, if there are repeated roots, okay, this is what you should do. So, what is an example of repeated roots is h of z equal to c0 plus c1 z inverse plus c2 z minus 2 divided by 1 minus d0 z inverse raised to the power 3. Okay, so basically polynomial by polynomial. Numerator polynomial has got order 2, denominator polynomial has got order 3. So therefore it is a proper rational form. However, there is a repeated root. Okay, this is, so this case, how do we write the partial fraction expansion? We write it as a1 divided by 1 minus d0 z inverse plus a2 divided by 1 minus d0 z inverse the whole squared plus a3 divided by 1 minus d0 z inverse the whole cube. Okay, and once again we have to compute a1, a2 and a3, and if you are familiar with it, I mean, you can, of course you can simplify it algebraically and then do that, but there is a very compact method that is given for us in Oppenheim and Schaefer. So you can refer to the method for computing a1, a2, a3, that is when you have repeated roots. There is a method given in Oppenheim and Schaefer in section 3.3.2. 3.3.2. All right. No, actually it is not a very difficult method. In fact, we will now go ahead and actually show you an example of how we can do that and make sure that we are comfortable in terms of our the ability to explain this. All right. So here is an example where there will be repeated roots, so that you will then see how to do partial fraction expansion even when there is a context of repeated roots. So let us look at this particular example. H of z equal to z cubed divided by z minus 1/2 z plus 1 by 3 whole square. We are given that mod z is greater than half. So that's an indication that this is going to be a right-sided sequence, and now we need to find a way to solve this. So let's write it in powers of z inverse. So this can be written as 1 minus 1/2 z inverse, 1 plus 1/3 z inverse the whole square. Okay. So I'm going to ask you to write the partial fraction expansion. So this is going to be a1 divided by the first term, 1 minus 1/2 z inverse. Now I'm going to have to deal with the repeated roots. So I'm going to call them as c1 divided by 1 plus 1/3 z inverse plus c2 divided by 1 plus 1/3 z inverse whole square. Okay, and either through direct simplification or through the method in Oppenheim and Schaefer, I would like you to verify the following results, that you will get a1 equal to 0.36, a2 to be equal to 0.24, 0.24, and a3 to be equal to 0.4. I'm sorry? Huh? Oh, C1, C2. Sorry. C1 and C2, sorry, thank you, yeah. So please go through and verify that you are getting these results, okay. So what we get is this is equal to 0.36 divided by 1 minus 1/2 z inverse plus 0.24 divided by 1 plus 1/3 z inverse plus 0.4 divided by 1 plus 1 by 3 z inverse the whole square. Okay. Now I want to do the inverse z transform. Very easy for the first two terms. Okay. What will it be? It will be 0.36 1/2 raised to the power n u of n. Okay. The second term, 0.24 into 1 by 3, sorry, minus 1 by 3, because we should be careful with the sign, minus 1 by 3 raised to the power n u of n. Okay, because the pole is located at minus 1 by 3. So basically the sequence will be minus 1 by 3 raised to the power n. Now of course the last part is this term. Again I want to take a few minutes to do the inverse z transform for this, so that it will be something that you will be comfortable with doing. Okay, how do we get the inverse z transform for this? So the first thing to note is what is the property that we have in the table. The property in the table is given by the result n times a of n u of n has got a z transform that is given by a z inverse divided by 1 minus a z inverse the whole squared. So you start by a power n u of n and then differentiate, and you get this particular result. So using this expression, then what I would like to do is the following. Okay, I'm going to rewrite this as 0.4 divided by minus 1 by 3 z inverse minus 1 by 3 z inverse. Okay, I'm multiplying and dividing by minus 1 by 3 Z inverse. And it will be clear in a minute why I'm doing that, because we're going to write this as 1 plus 1 by 3 Z inverse the whole squared. Then what we know is that this term corresponds to minus 1 by 3 raised to the power n u of n times n. Okay, n times minus 1 by 3 power n u of n is this term. This 0.4 is a scale factor. Okay, and what I have here is a minus 1 by 3, and the z comes to the top and it becomes a advance operator. Okay, z becomes an advance operator. So now I want to include this also. So I want to just sort of move this to the side. So I'm going to write this in the following form. Okay, I'm going to write this as 0.4 divided by minus 1 by 3 z times minus 1 by 3 z inverse divided by 1 plus 1 by 3 z inverse the whole squared. Now combine these two. What do you get as the expression? You will get n plus 1 minus 1 by 3 raised to the power n plus 1 u of n plus 1. Right? Basically, that's what this z is going to do. Whatever was the original sequence, you're going to advance it by 1 unit of time. Okay, and now basically what you're left with is the remaining term. So therefore, this particular expression corresponds to a time domain sequence which has got a scale factor of 0.4 divided by minus 1 by 3. The sequence is n plus 1 minus 1 by 3 raised to the power n plus 1 u of n plus 1. You can simplify it just one more step. This is the same as 0.4 n plus 1 minus 1 by 3 raised to the power n, because this and this will cancel, and what you get is u of n plus 1. Okay. If you're comfortable with that, we can go back here and write down that this term represents the following time domain sequence: 0.4 n plus 1 minus 1 by 3 raised to the power n u of n plus 1. Notice how we have used partial fraction expansion, the differentiation property and the time shift properties all together to get the result that we are interested in. So in a nutshell, basically the partial fraction expansion is a very powerful tool that we can use to get the results of the inverse Z transform in a way that we can handle.